Welcome back to The Explainer. Today we're taking a look under the hood at the invisible mathematical structures that literally power our digital world. Seriously, every click, every search, every single recommendation you see is governed by these hidden underlying rules. So let's just dive right in and uncover the foundational math that brings order to this massive digital universe of ours.
Here's our roadmap for the day. First up, we've got the power of relations. Then we'll look at organizing the chaos using posets. After that, we'll get into lattices and logic circuits, and finally, wrap things up by talking about designing ethical math solutions.
Okay, before we get completely lost in the heavy math, I want you to think about this for a second. How exactly does a database know how to optimize your query? When you're hunting for one highly specific piece of data buried in billions of records, the computer doesn't just guess, and it obviously doesn't read every single file one by one. Instead, it relies on a highly structured, logical map to instantly find the absolute most efficient path. The secret to how it actually pulls this off? Well, it lies right in the discrete mathematics we're about to explore.
All right, Section 1, the power of relations. Let's look at the basic building blocks.
So, in discrete math, a relation isn't just some vague, hand-wavy connection. It's a very strict set of rules defining exactly how different elements interact with one another. We map these interactions out using paths and digraphs, which, if you remember, are essentially directional maps showing what points to what. We also deal with different types of binary relations, plus equivalence relations that group together elements sharing identical properties. Ultimately, these rules dictate the very nature of connectivity in absolutely any network.
Now, you might be wondering, how do we actually find all these hidden connections in a massive web of data? Well, we use Warshaw's algorithm. It is this brilliantly logical step-by-step procedure. Step 1, you identify the direct paths, the obvious A to B links. Step 2, you discover the transitive connections. That just means if A connects to B and B connects to C, the algorithm is smart enough to figure out that A can ultimately reach C. And then step 3, it maps the complete network closure. This essentially reveals every single possible path, whether direct or indirect, within that entire diagraph.
And this right here perfectly illustrates why this abstract math actually matters to you every single day. Take social media networks or recommendation systems, for example. When a platform suggests a new friend or recommends a video it thinks you're going to like, it is literally executing operations on relations. It's using concepts like closures and Warshaw's algorithm to analyze the network paths and basically say, hey, based on this user's equivalence relations and transitive connections, they're definitely going to want to see this content. It's literally the engine driving your digital social life.
Moving right along to Section 2, posets, organizing the chaos. It's all about hierarchy and order.
Here's the thing, not all connections are created equal. Enter the poset, which stands for a partially ordered set. A poset basically takes a basic partial order relation and slaps a strict hierarchy onto it. It explicitly tells us what must come before what. Now, because this can get incredibly chaotic and complex in large systems, we visualize them using a Haas diagram. What's great about a Haas diagram is that it strips away all the clutter of those transitive paths we just talked about and simply shows us the direct hierarchical chain of command between elements. It instantly brings visual structure to a very messy web of relationships.
Now, inside these posets, you're going to find two totally different types of groupings, chains and anti-chains. A chain is exactly what it sounds like. It's a sequence where every single element is strictly ordered and perfectly comparable to the others. Think of it like steps on a ladder. You absolutely have to complete one to get to the next. An anti-chain, on the flip side, is a grouping where the elements are completely independent and incomparable. Neither one relies on the other to exist or execute.
Because we can parse out these chains, meaning tasks that must be done in a specific order, and anti-chains, meaning tasks that can be tackled simultaneously, we can achieve just ridiculous levels of efficiency. This is exactly how computers handle task scheduling and dependency management. And, tying it all back to our opening question, this is exactly how database query optimization works. The database essentially uses a poset structure to figure out which parts of your query have to be executed sequentially and which ones can be run independently at the exact same time. That's how it delivers your results in milliseconds.
Which brings us to Section 3, lattices and logic circuits. We are getting into some very strict structural territory here.
So a lattice basically takes the whole poset concept and locks it down with even stricter mathematical rules. In a lattice, every single pair of elements absolutely must have a unique upper bound and a unique lower bound. There's zero ambiguity here. There's a precise, mathematically defined ceiling and floor for every single relationship, which can then be broken down even further into specific types of lattices and sublattices. Oh, and as a quick aside, for the highly curious learners out there, a fantastic self-learning topic to look into after this explainer is isomorphism in lattices. It's a truly fascinating look at how completely different lattice structures can actually map perfectly onto one another.
Now, you might be asking, why on earth do we need that extreme level of structural rigidity? Well, it's absolutely crucial for things like Boolean algebra and logic circuits, which is literally the physical hardware logic inside your computer's processor. They rely entirely on these lattice structures to compute binary true and false states reliably. On top of that, information flow and security models depend heavily on lattices. When you're designing a secure system, you need absolute, mathematically proven upper and lower bounds to guarantee, without a shadow of a doubt, that sensitive data cannot flow into an unauthorized tier. Lattices give you the mathematical proof that your security model is actually sound.
And that leads perfectly into our final segment, Section 4, Designing Ethical Math Solutions. Let's talk about the real-world societal impact. It's super interesting because this actually pulls right from the core learning outcomes of studying discrete math, specifically outcomes 3.3 and 3.4. These demand that we use concepts like posets, lattices, and dependency management not just to make software run faster, but to actually design efficient and ethical solutions. When we build models for secure information flow or logic circuits, we're ultimately managing human data. We have a fundamental, non-negotiable responsibility to make sure our engineering solutions address the societal and ethical aspects of things like privacy, bias, and security. At the end of the day, it's not just math. It is quite literally the architecture of our modern society.
So I want to leave you all with a final thought to chew on. As we continue to build increasingly powerful algorithms governed by these relations, posets, and lattices, how do we ensure our mathematical models actually reflect our societal values? The math itself is totally impartial, sure, but the people designing the dependency management and the security models certainly aren't. Truly understanding these structures empowers you to do more than just write better code. It empowers you to engineer a fairer, vastly more secure digital world. Thank you so much for joining me for this explainer. Keep learning, keep questioning, and I'll see you next time.